Hey guys, I'm back with another video on PyTorch, and today we're gonna actually go through building a model and let's just take a look at each of the different layers we have and each of the different parts of our neural network. So in this video, let's first start off with doing our necessary imports like we do all the time, right? Import OS. Let's import Torch. And from Torch, we're going to import NN. And this allows us to do all our deep learning stuff and our neural network stuff. Okay, and let's also import a data loader. And if you don't know what data loaders are, or if you need a refresher, feel free to check out my video on datasets and data loaders. Okay, so let's import data loader. And like I said before, from Torch Vision, let's import datasets. And remember, we need to apply some transformations on our data, so let's import transforms. Okay, great, and let's run this. Okay, and it ran. Okay, so there are two things that we need to know. One is torch.nn.module and torch.nn.parameter. And inside our torch.nn.module, we have all the necessary things that are related to our network. And it has anything to do with your machine learning model and each of the different components that make it up. And so it's a really important thing that we're going to need to import. And yeah, so we have torch.nn.module, and this model, right, it's going to have some learning weights. And so if you need to deal with any of these learning weights, we're going to need to have torch.nn.parameter with us. And so if you have like weights and biases, which are an important part of your different computations, you're going to be dealing with torch.nn.parameter. And all of our learning weights are instances of the torch.nn.parameter. And if you want to access a list of those parameters, those long tensors, you can just call .parameters, and you'll see a full list. Okay. Great. So now let's just let's create a simple neural network. Okay. And our neural network is just a module. And when we say that our model has different layers, what we're saying is that it has different like submodules, and we can use those submodules to perform the different computations that are required for our model to really learn and train our data. And so, or train the model, sorry, to our data. Okay, so let's start off with writing our class, and let's just call it neural network. And it's going to be a child class of nn.module. Okay, and we have our constructor once again, init. Okay. And it's going to inherit from, well, the two parameters you can put in is just the name of the class, and the object, which is just self. And so we can put neural network, which is just the name of our class, and self, and colon it. Okay, great. And let's set our instance variables, or let's define them and declare them. So self.flatten is equal to nn.flatten. And we'll talk about this, don't worry. Or actually, instead of self.flatten, let's just start easy and talk about let's talk about linear layers, and let's talk about activation. Self.activation layers here. So self.linear 1. I'm going to set equal to torch.nn.linear. Okay, so these are the different components, and by components I mean like the different layers, the different modules to perform our computations. So linear is a layer that can do that, and let's pass in 100 and 200, and we're going to be talking about the parameters of each of these different layers. We're going to talk about more layers in a sec. Okay, so self.activation is equal to torch.nn.ReLU. Okay, and this is a rectified linear unit, and we're going to be talking about that as well. And let's have another linear layer, torch.nn.linear, and 210, and self.softmax is equal to torch.nn.softmax. And once again, we're going to be talking about this as well. And every neural network also has a forward method, and this is where the actual computation happens. So here we just defined our instance variables and all the stuff that we need, but we're also going to be defining a forward method. And so x is equal to self.linear. Okay, linear 1, which is what we defined here. Okay, self.activation. And we're setting x equal to the new x that we get once we pass it into this layer. So it's like a machine, and just think of it as like a machine, like box or whatever, and you have x. It's just like algebra. You have x and you pass it into a function and you get a new value. And so we're going to be setting that equal to x, and which is one of our parameters here. And so self.linear 2, and x is equal to self.softmax. Okay, x, and let's just return x. Okay, and let's create an instance of our neural network. Remember, this is just a regular Python class, and this is just a regular, and because it's just a regular Python class, we can write the methods like that as well. Okay, so now let's go on to talking about the different layers that we can use in our model, depending on the different type of data, depending on what you want to do. You can use different layers. Okay, so the first layer that we're going to be talking about is the one we mentioned here, which is the linear layer. Okay, and the linear layer just applies some regular linear transformations. And remember, machine learning has to do a lot with like mathematical functions and modeling those and simulating them. And so linear just means the regular linear you all know and love for math. And so yeah, it applies some linear transformations on it. And what this means is that, so when you have like some inputs, you pass it through a model and you get some outputs, and you have different layers. And if it's a linear layer, then every input is going to be connected to every output. And you call this a linear layer, or you can also call it a fully connected layer, because each of the inputs are fully connected with each of the outputs. And we're dealing with tensor operations here. And so if you need a refresher on tensor operations, you can feel free to check my video out. And I mean, it doesn't need to affect, all the inputs don't need to affect the outputs equally. I mean, it depends on your weights and biases. And so yeah, and if you're confused on what weights and biases are, I'm not going to go through them in detail too much, but like if you have an equation, right, like y equals mx plus b, your m, it's like you can actually write it as y equals wx plus b, and your w is going to be the weight, and the b is just going to be your bias. And so that would be like that. And if your model had m inputs and n outputs, the weights would be an m by n matrix. Okay, so let's go through an example, a quick example, not going to be too much. But if you have something called linear and you set it equal to a linear layer, okay, 3, 2, and yeah, and if you create something called, if you create an x, it's going to be a random tensor, 1, 3. Okay, this is going to be our input. Let's make this our input. Okay. Okay. Print x. Okay, and by the way, like, our inputs are tensors, right? For example, if it was an image, it would be a tensor, right? That's how you would represent the image. Okay, and let's print our weights and biases. Okay, and these are parameters like I talked about, and they would be instances of the torch.nn.parameters. Parameter. Okay. Okay, and let's loop through this. Let's say for every parameter, in our linear layer dot parameter, remember I said here, you can use the dot parameters function and you can call it, and then you're going to get the different parameters. And so let's just print our parameter. And let's set the output. Y is the output, x is the input. And let's set our output equal to our changed input. So it's going to be our input passed through the linear layer, and we get our output. So it's going to be passing through the linear layer. Okay. And let's print our output. Okay. Print y. And so if you run this, you get our input. Our input is a random tensor, torch.rand, of shape 1 by 3. we have weight and bias parameters, and we get these parameters. Okay. And you're doing a matrix multiplication by the weights. Okay. And so if you do a matrix multiplication 1 by 3 and 3 by 2, okay, due to some broadcasting here, we can get a shape of 2 by 3. Okay, and yeah, so, and also the requires grad equals true. That has to do with autograd, which we're going to be talking about in our next video. And I guess it kind of makes sense that we have like a forward method, because in autograd we're going to be calling a dot backward, and what that does is it calls, it just goes back every computation and takes the derivative, or the gradient, and yeah, we're not going to be talking too much about that now. Okay. And, yeah, and so one pretty common place you'll see linear layers, are classifiers. So if you have like a model that does some classification, you're going to be seeing a lot of these linear layers. And the n, which is like if you have an n by n matrix, and the n, if the n is the output, you're going to be, it would typically have n classes in the classifier model. Okay, so great, we talked about the linear layer. There are other layers, obviously, and one layer you may or may not have heard of is the convolutional layer. Okay, so convolutional layers, what are they good for? Well, if you have, let's say an image, you can use it in other places as well, but if you have an image, so the things that are important to notice in this image are probably different like patterns, right? And so you're not going to notice a pattern if you look just at one pixel, right? You're going to need to look a little bit more broadly, and like maybe not the entire picture at once, but like little small spots, and like the pixels around the thing that you're looking at matter, and so that's where you would use a convolutional layer to help you in that process. And yeah, so they handle data with a high degree of spatial correlation, like I said before, and we use them often in computer vision. But another place you can use them is in NLP, which is natural language processing. And so if you have a sentence, you could decipher the meaning of that sentence, or not you, but like the model could decipher a meaning in that sentence, not only by looking at a specific word, but also looking at how the words are grouped, and the relationship between a word and the words nearby. So that's what I mean by spatial correlation, and that's where convolutional layers can help you. Okay, so you know how we had like torch.nn.linear here? Well, I'm not gonna write an entire class, but we can talk about the different layers, which are conv 2D, we can have conv 1D, conv 3D, depending on what you need. But yeah, let's go through it then. We can have like self.conv1, equal to torch.nn, and all of these layers, they come from the NN module, right? It stands for neural network. And so we have conv2d. And honestly, these functions and these layers, they make things a whole lot easier, because like otherwise you would need to come up with the code to actually like find meaning in the images or your text or whatever data you're dealing with. So it's pretty neat that we have these interesting functions. So you can also have conv2d instead of equal to torch.nn.conv2d, which is basically the same thing we did, but we're adding two convolutional layers. And we could add a few linear layers if we wanted to, but we already covered that, so linear, we don't need to talk too much about it. Okay, and by the way, it's not just like parentheses, you have parameters in them. Actually, you know what? This whole thing would be a lot easier if we just had a class to deal with, right? So let's create a Linnet. Okay, let's do one import first. Okay, but let's create a Linnet. A Linnet is one of the first neural network model, I believe. Okay, but okay, so like we did before, we're just going to create a class. Let's call it Linnet. And torch, it's going to inherit from torch.nn.module, like the other model did. Okay, we create our basic constructor. It's going to take in self. It's going to, oh, I didn't mean to run it just yet. Okay, and we're going to use super. Okay, Linnet. Okay, comma self. Dot init, like we did. And let's put our layers here. Okay. Okay. Great. And so the parameters that you would put in are the image channels. Okay. And so one is going to be color. Let's just deal with black and white here. So maybe the color is going to be 1. If they were like actually in color, then you would put 3 color channels for like red, green, and blue. But let's just deal with gray for now. So it's going to be 1 and 6 output channels. And let's do a 5 by 5 like convolution, okay, matrix. And this video is just meant to be like an overview of the different layers. We're gonna go like deeper into the actual deep learning aspect of it in another video, and we're gonna be talking about like how the model like skips over, or maybe not skips over, but in some cases it does, but like how it moves across the matrix to find the different features, and how if you wanted to you could skip it, or like the step size and whatnot. We're going to be talking about all that good stuff in another video that's mainly focused on the deep learning aspect. But here I'm just going to introduce to you that deep learning idea and like how we have different layers to help us with that. And so we can do 6 comma 16. It doesn't really matter which you put in, what you put in the features parameter, and we're gonna be talking about that in just a sec. Okay, so 3. Okay, linear layer. Okay, it's gonna be the 16 times the 6 times the 6. Okay, and 120. You'll see why, I promise. Okay, self dot. Let's just create one more linear layer. Actually, let's create 2 more. So torch.nn.linear. 120, 84. Self.lin3. Lin just stands for linear here. Linear and 84 by 10. Okay. So what do these mean exactly? All right. So Lynette, like I'm not creating Lynette is not like my novel idea, right? Lynette has always existed. Well, not always, but it's not a new thing. So Lynette usually takes a 1 by 32 by 32 image, which is why I put a 1 here, which is why it's a grayscale image. And how many input channels you want is going to be the first parameter. And so it's 1, right? Like I mentioned before. If I had color, it would be 3. And you know how I said that like a model would go through the image to check for features? Well, you can specify how many features you want it to check, and in this case, I've picked 6. You could have picked 7, you could have picked 8. This number does not matter. It can be of your choosing. And so a convolutional layer is going to be like a square, and it's going to go through your image. It's going to just check for the features. But how big is that like that square that we want to check? Like it's going to be so you have an image, right? And you have a little convolutional layer that just goes through the image 1 by 1, or maybe like 5 by 5 in this case, right? Yeah, so that convolution just scans through your image. It's a square. And so the size of that square, I'm saying, is going to be 5 by 5. Okay. And this is also the kernel size. So however big that window is that scans through your image, which is your convolution, that you call a kernel. Okay? And this is the kernel size. It's 5 by 5. Okay? And if you didn't want it to be a square, if you didn't want it to be 5 by 5, you could have put a tuple in here, saying like 5 by 2 or 5 by 3 or something like that. Okay? And so what happens when you pass your input through a convolutional layer? Well, you get something called an activation map. And so the activation map just maps out the features that it just that your model just discovered and like broke at. And so that's what our second conv2d is. Wait a sec, did I put? Or yeah, conv1 and conv2. I don't need the d here because I already have it. And so the output tensor of the first conv1 is going to be 6 by 28 by 28. And we have a 28 because remember we have a 5 by 5 like window for our convolution. And remember Linnet, I should have mentioned it here. It's like a 1 by 32 by 32 image. And when you go through that image with a 5 by 5 window, you're like our output tensor is going to be 28. Like if you like check it out, you'll get a 28. And yeah, we pass, you see ReLU. Well, I didn't write that yet. So let's write our forward function. Def forward, okay, self, and our input. And like we did before, we're just going to say x equals the new x after we've passed it in through a layer. And so we're going to say x is equal to f dot max pool 2D, okay, f dot ReLU, and self. Self just refers to the object once again. Self dot conv1, we pass in x 2 by 2, and we'll talk about these parameters. Okay, and we can have x is equal to f, and remember the f is our torch dot functional, and so, like, I don't want to go into this too much, but I just want to let you know that, like, we have x is equal to these series of operations and computations. We're going to definitely go into convolutional neural networks in another video. But the main takeaway here is that we have an activation function, which is really like it's basically just a mathematical function. And so if you have your basic linear layers, which we've talked about in a model, the whole thing is just going to be linear, right? There's no real complex math going on. And so if you want to bring some complexity and some non-linearity instead of just keeping everything linear, because then if it was all just linear, then everything could be settled with just one matrix multiplication, and deep learning is more complex than that. So we're going to need an activation function to spice things up a bit, and so not every output needs to be connected to an input, or vice versa. And so there's more like, it's more like a web now, like something's going here and then there and then here and then there. And so the relationship between the input and output is going to be a bit more complex. So that was the main point. And our so that's what the activation function does. What does the max pool do? Well, the max pool, what that does is that, so we have our activation map, right? Once we've passed it through the first convolutional layer, well, we have an activation map, and we have the different features like spatially mapped somewhere on the activation map. But you have too much data now. Like, is there any way we can reduce that data down, just not completely so that we have zero data, but just like a little bit, so that it's not so much to manage? And so when we go through the image, once we scan through the image, we have some intermediate tensor computations, right? That's what it's doing when it scans. It doesn't just like look with its eyes, right? We do some computation, and so once we have a tensor for each one of the scans, we can take a max value out of each of the matrices and boil that big thing down to something a little smaller, more manageable. So that's what the max pool 2D does. You can also have an average pool, so it takes the average of those values, or some other pooling functions. Okay, pooling layers rather. Okay, so that's what's going on. Okay. Great. So I don't want to spend too much time on that, but I hope you've got something out of it. So let's move on to recurrent neural networks. I mean, not neural networks. Let's just talk about the layers for now. Recurrent layers. Okay, so unlike convolutional layers, which have to do with what's going on, like in space, or what's going on around a certain point or value or word, recurrent layers deal with sequential data. And so if you have another type of data which aren't images, but rather like time series, like you're doing an experiment and you have data on like the different times you did something, you're doing something repeatedly, and you want to monitor something over time, and like time is sequential, right? So we can use recurrent layers for that. We can also use it for natural language sentences, or another sequence sort of thing like DNA, or anything to do with genomic data. So those are the different purposes and use cases for recurrent layers. And the way it does it is, the way RNNs, or recurrent neural networks, do this is by having this sort of hidden layer. And if you haven't heard of hidden layers, you have now. So this hidden layer just remembers what it's seen in the sequence up until that point. And so it keeps like a log of like, hey, this is how much time has passed now, and this is what has happened at every point in time, or whatnot. But it's not immediately relevant to the current computation. I mean, it is, but it's too much to handle at once, so it's like a hidden layer. And so yeah, so that's what recurrent layers are like. But it's kind of complex, I have to say. But yeah, it's kind of complex. I'm not going to go through it in this video. So we have convolutional layers, we have recurrent layers. And by the way, LSTM networks, there's an excellent tutorial on pytorch.org that incorporates some of this, like these recurrent layers, and I would definitely recommend checking that out. Okay, great. Okay. We've talked about max pooling. And another thing we could talk about are dropout layers. And okay, let's just keep a note. I forgot to do that. Okay. This again has to do with like cutting down on the amount of data that you have, just by like dropping entire parts of your tensor and setting them to 0, and you can select the probability as well of how much you want to be set to 0. Okay, so you can have like a tensor is equal to a random tensor, okay, and these are the dimensions. Okay, and we're going to change it up a bit. Okay, and you can select how much you want to drop, like I said before, and that's going to be set to P, or P is going to be set to that. And if you want like 0.3, so like 30% of them to be set to 0, actually it's not the percent, it's a probability. And so yeah, if you don't specify a value, the default's going to be set to 0.5, so 50%, or 50%. And let's just print dropout. Okay, and by the way, this you would pass in tensor. So this is also the reason why I'm not just printing dropout, is because like this is a neural network component, and like all the other layers that we've had here, you pass in the value, you pass in the input to the layer, and then it's going to do some computation. So if you print it, you see 1, 2 of them. If you wanted 0.8, you're going to see a lot more zeros. See? Like these are all zeros. Okay. So we've talked about activation functions, right? The last thing I want to talk about are loss functions, which just measures how far you are, how far your output, or how far your predictions are from the actual output. And PyTorch offers a lot of loss functions, including cross entropy, and cross entropy loss, mean squared error. There's a lot of math going on behind it. So, and another one is negative likelihood loss. Okay, and we would use that more often in like classifiers. Okay, so let me just keep a note of what we've talked about, because I know I didn't create a heading for everything. We talked about linear layers, we talked about convolutional layers, we talked about recurrent layers, we've talked about activation functions, okay, which reduces your data by finding either the max, average, of like those windows that we've talked about. Okay, so we have activation functions. Maybe not that big, but okay, activation functions. We've talked about dropout layers, and we've talked about loss functions. Mean squared error. And negative likelihood loss. Okay. Okay, great. And another transformation you could apply, let's put this a little up here, is something called flatten. And what flatten does is it takes your image, which is a tensor, which is has more than one dimension, right? And it puts it into a string, or like of just like a continuous array of like however many pixels you have. And so an example of that would be nn.flatten torch.nn. If we said import torch.nn as nn, oh, wait, never mind. Okay, we already did, so okay. Flatten. We don't have an input image. I mean, we can create an input image and set it equal to torch.rand 3,28,28, which is the image size of a fashion MNIST image, and the 3 once again is your color channels. And so if we have flatten, and if we pass in our image, and we print our image, not our image, but rather our image size, so that we can see that continuous array. Okay, image.size. Okay, 3 by 3. Okay, we didn't set it equal to image again, so. Okay, 3 by 784. Okay, you see, it made it one long array. Okay, and one last thing we didn't discuss actually is the nn.softmax. And so the nn.softmax just allows us, instead of getting the specific values of the tensor, it gives us the probabilities of the certain image. I'm just talking speaking in the context of like images right now, but it can work for any classifier. But it gives us the probabilities of what this image could be. So if the model is pretty confident, then the first choice would probably be 0.9, and that's what the softmax would tell you. Okay. And there's an nn.softmax module. So yeah, definitely read the documentation for that. It's quite helpful, but don't worry, like this, I know this is, like, I know there could be a lot more information that I could put in this video, but, we will deal with that. We'll dive into, like, actually building models. I know this was a model, but this was just a test. We'll go into a real example, in another video, and dive deeper into each of the layers and see them in action. Okay? So, yeah, I think that's it for this video. I know we went a little long. But yeah, thank you so much, and I hope you got something out of this video. And don't forget to like, comment, and subscribe. Yeah, thank you so much. Take care.